So, hello everyone. Hope you're doing really good and welcome back to my channel. So, today we are at the July day 11 daily Leetcode challenge, and we again have a question on trees, and it's on the medium level side. But definitely, I felt that these kind of questions are really interesting to solve, and they will give a different dimension to an understanding of what trees are and what possible ways to solve questions based on trees. Okay, so this particular question, like unlike the yesterday's question, it's definitely on more on the deeper side. Okay, we'll have to get a lot of understanding to think such an approach. Okay, because in this kind of question, totally the structure given to us, we are changing it. Okay, so that's why I will say please pay attention here, and definitely what you are after solving this question, you will have a different method to approach every question. Which whenever you see a question on tree, you will have a different dimension to it. Okay, will add different dimension to your thinking. That's what I wanted to say. So please pay attention. Here we are going to alter the structure of the tree to get answer. Okay, we'll see that. First, let us see the question. It's question 863. All nodes distance k in a binary tree. So it's given that it's a binary tree. That means any particular node cannot have more than two children. Okay, and we have to find all nodes which are at distance k. What it means, we'll see that. So here you can see the input is the root of the tree. Okay, input is the root of the tree. There is a integer target and integer k given to us. Okay, so remember one thing, the target which you are seeing here, it's written as 5. Okay, it appears to us as an integer, but basically this is also not an integer. So you can see there is a class called tree node class. Okay, root is also object of tree node class, and this target is also object of tree node class. Okay, so please pay attention here. Initially I also thought it's an integer, but it's not the case. Okay, it's definitely not the case. But yeah, k is integer. K is definitely integer, no doubt in that. Okay, if I can, yeah, do that. K is definitely integer. Okay, yeah. So please pay attention. If you are a beginner, then definitely you should be understanding what a T-node class is. So any object of this particular class is going to have these many values. Okay, it will have a called data member called dot val, which will store integer. Then it will have two pointers, left and right pointer. Okay, to point to its left and right children. Okay, but as you will see, we will add another data member here, another pointer here, which will point to its parent. But we'll see why we need that. Okay, we'll first come to the theory part of it, then we'll go there. So the question is, given the root of a binary tree, you can see here the root is given to us. Okay, the root is given to us. It's object of tree node class. Okay, given the root of a binary tree, the value of the value of a target node target. Okay, here is the target node, which is also a node in this particular tree node class. Okay, it's a particular object in a tree node class. Okay, given the root of a binary tree, the value of a target node target and the integer k. Okay, return the array of values. Remember, they're asking values, they're not asking pointers to the objects. Okay, they're just asking values. Return the array of the values of all nodes that have a distance k from the target node. Okay, so for example, they're talking about 5 here. Okay, first please pay attention to this example. The target is 5 and the k is 2. Okay, so we can see what are at a distance 2. Okay, we can see that 7 is at a distance 2 from 5, 4 is at a distance 2 from 5. But if we go on the top, okay, if we go from 5 to 3 and then we come down, so 1 is also at a distance 5. Okay, none of the other nodes are at a distance 5. Okay, so what we have to do, we have to return the value of these nodes. What are the value of these nodes? 7, 4 and 1. Okay, you can return the answer in any order. That's what they are trying to say. Remember, we don't have to return the pointer to these these particular nodes. Okay, 7, 4 and 1, we just have to return the values. Okay, 7, 4 and 1, these are just integers. Okay, you can please see the return type. Okay, the return type of the question says that a list of integers. Okay, not a list of tree node objects. Okay, so I hope this question is at least clear to you now. So one thing is very clear: whenever the children are at a certain distance, we can know that. Okay, we can do a defense and we can get to know that. But see, the pointers are in such a way arranged here that we can only go down. Okay, we cannot go up. Okay, that's what the problem here is. Okay, we cannot go the way we want along the upside. Okay, we can backtrack, but backtracking will also happen in a certain direction only. Okay, so what will happen is, see, I can come to 3, but after 3, I cannot backtrack to 1. Okay, we have to follow a pointer here. So it will be a combination of backtracks and going through the pointers. So what additionally we can do is that, see, this is the question given to us. See, we cannot go from 5 to 3. Okay, see, suppose I want to go from 5 to 7 and 4, that can be done. Okay, that distance can be calculated, but I need to do the distance in other ways also. Okay, for example, in the top way. Then coming to the children of that, okay, we can go even above 3 if it's not a root. That also needs to be done. Okay, so cannot get into the parent node. So what we need to do is we need to add a pointer for each node to its parent. Okay, add a pointer to each node to its parent. For example, from 6 we can go to 5, from 5 we can go to 3, and from 1 also we can go to 3. So the idea here is now every kind of traversal will be possible. Okay, that's what we are actually trying to do here. Okay, So let us see how we can do that. So in Python, basically, please pay attention now. This is the coding part. Now in Python, what can happen is that once you have created a class and once you've created this object, still you can add a data member on the go. Okay, you did not alter the code in the class. Okay, see in the class, in the definition of the class, there are only two pointers defined. But in Python, we have this freedom to, after the object of a class is created, we can add a data member, and that is what we are going to do now. Okay, so please pay attention to what I'm saying. Remember, in C++ and Java, these things are not possible. Okay, so for this particular question, Python will be a definitely helpful language if you are doing these things in Python. Okay, if you try to do it in C++, you may have to create another class, and you may have to migrate all the objects of the tree node to another class and do that. Okay, so for your easiness, I am doing it in Python. Okay, what we'll do is first recursively we'll add the parents. What we'll do, see, very simple. I will created a function like this. Okay, I will call it with the root and none. Okay, remember, the root of the tree do not have a parent. Please pay attention to this. The root of the tree do not have a parent. That means whenever the parent is none, we should not add a link to it. Okay, so I'm calling this function with the root and none. Okay, what we'll do, we'll first check if the current node is none. Okay, if the current node is none, do not do anything. Okay, do not do anything. Otherwise, what we need to do, okay, we are adding this new pointer. Okay, cur dot parent. See, for example, current is a node. Okay, node dot left was there previously, node dot right was there previously, node dot well was there, because these are data members. Similarly, now we are adding no node dot parent. Okay, cur is a node. I'm adding node dot parent as a new pointer to this object. What is this object? This object is a object of this particular class. Okay, so what I'm doing, I'm adding a new pointer. Node dot parent is equal to, it will point to this. Okay, we are parenting the parent also in every case. Okay, it will point to the parent. Okay, so in the case of the root, the parent will be none. Okay, in the case of root, the parent will be none, as you can see here. After I have done this, what I will do, I will traverse the graph. Okay, I will go down and I will do that the same. Okay, so now I will call the same function on its left and right children. Okay, these are the left and right children of the current node, that is the cur node. What I have done for the current node, I have made a link to its parent. Okay, now I am doing the same thing for its children. Okay, so it will go and call the same function for its children. Okay, what will happen, for example, see, 3, I will add a link to its parent, which is none. Okay, then I will call the function 5 and 1. 5 will add a link towards 3, 1 will add a link towards 3. Okay, it will be shown here. Okay, 5 will add a link towards 3, 1 will add a link towards 3, then it will call it for its own children. Okay, then 6 will add a link towards 5 and 2 will add a link towards 5. Similarly, 0 will add a link to, then the same thing will continue, right? I am hoping that you are understanding what I'm saying. That's, see, for every node we are doing it. See, we are going from down the order. Okay, it will start from 3 and it will go down the order. Okay, first all the children of 3 will be covered, then all the children 5 of 1, and that means at a distance of, after the first iteration, all the nodes at a distance 1 will have it pointed towards its parent. Then after the second iteration, all the nodes which are at distance 2 from the root will have a pointer towards its parent. That's how it will be functioning. Okay, this will happen in a BFS approach. Okay, these things will happen in a, let me not call it as BFS, but it's happening recursively. But if you see overall, see, initially what will happen is, first the left child will be called, the left child will have a parent, then it will call its own left child, so 6 will have a parent first, then it will complete right child. So that way it will happen. So it's not a BFS approach, but if you see how it works, that's how it works. Okay, after both the iterations are, that means after these two functions are completed, all the nodes at distance 1, then at distance 2, and then at distance 2 will have a pointer towards its parent. Okay, now coming to the important part, this is the answer. Okay, this is going to be this answer. Okay, it will show integers. Okay, I'm creating node visited because I do not want to visit the nodes again. So what my strategy will be, what I will do is, see, suppose I'm at 5. Okay, I want to know all the nodes which are at distance 2. Okay, what I will do, I will go through all possible directions. Okay, what are the directions? I will go to 6, I will go to 2, and I will go to 3. Okay, then one distance 1 will be used. Okay, so we have used the distance 1 to reach here. Now I want all the distance at 2. Okay, so for 2 also I will start the same. Go to one distance beyond. Okay, 7 and 4. Definitely 7 and 4 are distance 5. So stop and return back. Okay, it will go to 3. 3 is a distance 1. Definitely I can go for one more distance. So go to all possible. So it can go to its parent. If 3 has a parent, it can go to that, or it will can go to its children which are not already visited. Okay, so it can go to 1. 5 is already visited, it will not go to 5. Remember that. So what we are doing is, see, there are 3 approaches possible here. Okay, 3 dimensions possible. So for example, 5 will call for the, go to both of its children, and 5 will go to its parent. Similarly, 2 will also go to its all both the children, and if it's a parent, and all the ones which are already visited will not be visited again. Please pay attention. There are 3 things possible. 5 can go to both of its children, and 5 can go to its parent. Okay, Remember, whichever is visited again will not go to that. That means 3 will not again come back to 5. Similarly, 6 will not again come back to 5. 2 will not again come back to 5 because we went from 5 to 2, right? So 2 will only go below. Similarly, 3 will only go to the other children which is not visited. Okay, that's what the idea is. And similarly we'll get to the answer. Okay, so that's what we're doing here. We're defining a function called dfs. Okay, the dfs we're starting with, what will happen is, see, we're starting from the target. Remember, target, I'm again saying this because this mistake many of you will do. You'll think the target is a number and not a tree node, and you will be wasting time in searching for the tree nodes index. Okay, tree nodes link to the object. So T node is a target, is a T node basically. We are starting the defense function from the target, and I'm passing k as a parameter. So what we'll do, we'll check if the current node is none. In case it is none, or in case it is already visited, okay, return. Do not do anything and simply return. If the current node is none, or the node is already visited, any of them, or remember the condition or is coming, return back. Okay. Now we will first add the current node to the visited set. Okay, this is the set we are using, right? Then remember we are passing the distance k initially. Okay. Okay, we'll come back to this function later, but see that these things well. Okay, as I've mentioned, there are three ways now. Okay, there are three ways to traverse. First is going to the parent. Remember we are reducing the distance. Whenever we're doing a traversal, we're reducing the distance. Okay, I can go to my parent. I can reduce the distance by one. I can go to my left children. I can reduce the distance by one, or I can go to my right children. I can reduce the distance by one. Okay, so whenever I'm going to another node, I'm reducing the distance. Okay, so what will happen when I come to the node which is at distance two, that is at a distance k? What will happen? The distance will become zero. Okay, for example, see here I'm starting. Okay, I can come to 6. Now the distance will remain as 1. I can come to 2. Now the distance will remain as 1. When I go from 2 to 7, the distance will become 0. Okay, that's what we are checking here. If the distance becomes 0, then definitely the current node is at a distance k from the target node. Okay, I can add its value. I can add the value of the current node to my answer array. Okay, this is how it will function. As I mentioned, there are three ways. I can either go to my parent, or to my left children, or to my right children, and I am reducing the distance at every instance. Okay, you can see that distance minus 1 in all the three. Okay, so whenever the distance becomes 0, that means the node at which the distance becomes 0 is at a distance k from the target node. I can append the value of the node to my answer. Okay, this is my answer. Then I can turn the answer. If you talk about the time complexity, see, ultimately we are using this set, right? This ensures that we do not visit any node more than once. So in the worst case, we would have visited all the nodes. Okay, so it's often, and because we are using this particular data structure, so the space complexity also will be often. So the time and space complexity are often. So we are friends. We learned one thing today, that with the given the data structure, we can add more links to it in Python without getting errors. Okay, in the same seats, it will still remain object of that class only, but we are adding a more data member to it on the go. Okay, even after the class is created, even after the object is created. This is the only new thing which we learned here, and this will add a new dimension to how we see the problem the next time. Okay, so please remember this approach. It will help you in a longer run. Okay. So yeah, friends, hope you have enjoyed my solution. Hope you have understood my solution. If you have enjoyed, please do comment below. And yeah, we'll again meet tomorrow. Thanks a lot.